Hello everyone. So today for the second half of the lesson, we are going to look at very quickly the last Newton's law there is, which is the Newton's third law. Okay, so Newton's third law states that for every action, there must be a equal but opposite reaction. Okay, so for every action, force, there is an equal. Now, equal in what? So if you apply a force to something, there is always a reaction. So it's equal in magnitude. Okay, so equal in magnitude, but opposite in direction. So equal but opposite. So the opposite part is in direction. Reaction force. Okay, so for every action, there is an opposite, equal and opposite reaction. Now, we call these type of force pair action, reaction, force pair. Okay, so for example, one of the example for this kind of problem you have already studied, which is the relationship between, for example, force of gravity and normal force. Okay, so force of gravity is the action force. So you, as a box, apply a force to the ground. So the ground apply a reaction force opposite to you. And the reaction force is equal in magnitude, but opposite in direction. So you can think of the force of gravity as an action force, and the normal force is the normal force in here. Now, but it turns out that every force, not just gravity, every force can actually give rise to a reaction force, not just gravity. So for example, if you have a baseball bat, right? So let's say you have a baseball bat, and then you hit a baseball with it, okay? So the baseball bat applies a force to the baseball, which is the applied force. So that's an action force, right? So the bat, so you have your action in here, which is the bat hit the ball. Okay, now, then what is the reaction? The reaction is that the ball actually hits the bats too, if you take the opposite point of view, right? So the ball hits the bat. So the bat hits the ball hits the bat, depending on which way you look at it. So if you look at it from the perspective of the bat, we might call it applied force. But what is the force pushing back at you when you hit the bat, when the bat hit the ball? That is the electron of the ball repelling the electron of the bat, which is actually called normal force, right? So technically, now, another example you can look at with this is, for example, when you start running, right? When you start running. Now, the reason why people can actually walk or run, so when you think about what happened is that so let's say you have a person and he is going to attempt to run forward, right? Okay, if you actually get up right now and try to walk forward, pay attention to your feet. Which way, in direction, does your feet actually push against? Which way? Do you push forward? Which way is the force that you actually apply on the ground? Think about it. So let's say you are standing up right now and you are applying a force forward. Which way does your body go? If your feet is pushing forward on the ground, your body actually goes backward, right? So if you want to go forward, you actually need to push your feet backward. Well, how does that work? You're pushing backward. How come you're going forward? Well, that is also a action-reaction force, a pair. So in this picture, so let's say, the ground is over here. So you're actually, every time you're walking, you're pushing with a force going backward. Okay, so this is your face, and you're trying to walk this way. Okay, you're always pushing backward in order for yourself to move forward. Now, how does that work? Well, we have to look at your feet. Right, we have to look at your feet. So this is your feet, on the ground, and this is the ground right here. Okay, so the feet and the ground right there. Now, okay, so you apply a force backward with your feet. If you try to move to the right hand side, then the force that you have to apply must be going to the left hand side. Now, then at the same time, there is actually a force pushing you forward, and that's why you are able to accelerate forward. But what would that force be? Okay, think about it. Now, one thing we can look at from here is looking at this picture. What else is there? Of course, you have force of gravity. Of course, you have normal force. But these two forces are internally cancelled, so they don't really count. What else is on this picture? Now, if this is the free body diagram, and that's it, right? Then obviously, this whole thing is not balanced, and your feet should be going backward. So what is this force that's... Now, obviously, when you're walking, the feet that is actually touching the ground is not moving during that time, right? So your body is going forward, but then your feet is actually not moving. Like for a moment, when your feet actually touches the ground and you push against the ground, your feet is stationary. You notice that? So that means at that moment, Newton's first law says, there should be no net force on your feet. And now if you look at this picture, there should be a net force on your feet, which is Fa with no one balancing it, right? So there must be something balancing Fa. There must be something balancing Fa. Now, some of you might have guessed it already. This picture is missing friction because the ground in your feet has friction and you have normal force and you're rubbing against the surface, so you will have friction. But what a lot of people don't realize is that this friction is exactly the same amount as your applied force. So, when you think about it, so that's the reason why you're not slipping when you are, if the ground that you're walking on is rough, you have a better grip and you are able to walk forward without much effort. But imagine what happened if you're, for example, trying to walk on ice. Why is it so difficult to walk on ice? Why do you fall down during the winter when you accidentally walk on black ice? Well, because ice has a very little amount of friction. So you try to walk on top of it by pushing yourself backward. The amount of friction that the ice can generate is not big enough to keep your feet maintaining at that location. So what happened is your body, your feet won't be able to stay in one place. So then you slip and you fall, right? So that means even though frictions is a very bad thing when you think about it, because it makes everything slow down. But without friction, this world will not actually function. Without friction, you cannot walk properly. Imagine that you are born on, let's say you're born in a world where there's no frictions at all on any surfaces, right? You won't be able to go anywhere. If you're born in the middle let's say you're born in the middle of the room, you'll be forever stuck in the middle of the room. Without any frictions on the ground, you won't be able to walk anywhere or crawl anywhere, because no matter what you try to do, I don't think you will be able to stand up either. Standing up, walking, crawling requires at least a little bit of frictions between the surfaces that you're touching and your hand or your feet, right? In this case, your hand or your foot. So, thank God there is friction on the ground. Otherwise, you won't be able to walk. Or maybe someone push you and you walk, you won't be able to stop. Stopping also requires friction. If you're running really fast and you try to stop, that also requires friction. Okay, so what is the force pair in this situation? So a sprinter start running. So basically, the runner pushes the ground. So that is one force. So the runner pushes the ground, and the ground pushes the runner. Okay, so that's the force pairs. Now, the third example is when a fish, okay, so a fish is swimming. So, or when you are swimming, you think about the experience of you going swimming, right? Which way do you push the water? If you're trying to go forward, think about it. Do you push the water forward? No, right? You have to push the water backward. Then your body goes forward. That is also a action and reaction pair. So the fish does the same thing. They use their little fin to push the water backward. So they apply a force with their muscle to the water. So that's your apply force. And then in turn, what happened is that the water will apply a force to the fish, which push the fish forward. Okay, so any force, for every force that you apply, there is always an if that force is touching any type of subject, for example, like the ground or anything, there's always an opposite, equal but opposite reaction force. Okay, so there's always an equal and opposite reaction force. So when you're pushing, like for example, a wall, the reason why the wall is not falling back is because, or falling down, is because your apply force is the same as the normal force from the wall pushing you back. So the action and reaction force pairs balance out and nothing is moving. Okay, so now imagine when you're driving sometimes, I'm sure you've seen that before. You're driving and suddenly you hear this pop noise on your windshield and you look at it. Oh, there's a little dead, for example, maybe mosquito or dead bugs, dead flies, dead, grasshoppers, right? You hit a bug. Now, what force pairs occur? So the truck, okay, so we have a semi-trailer, which is a truck, hits a bug. So the semi-trailer. So now, how heavy is a truck? Maybe like a couple thousand kilograms, right? Maybe like 2,000 kilograms. So how about the bug? So the bug is like here. So here's the little bug there. Okay. So the bug is much, much lighter. The bug is like a few grams. So the mass of the bug is only a few grams. Maybe it's 10 grams. So 0.01 kilogram. Okay, so your car is driving really fast so that it hits the bug by accident. So when you hit the bug, so what happened is you apply force to the bug. So maybe because you are very massive and you're moving very, very fast, the force would be, let's say 1,000 Newton, right? Like 1,000 Newton. Okay, so this is the force that the truck hits the bug with that force. Now, but at the same time, the bug also hits the windshield of the truck. Now, sometimes when they actually hit so hard that people will have a cracked windshield because they hit like a grasshopper flying in the air, which is very unfortunate, but it happens. Okay, so the bug also hits you back. Now, but according to Newton, these two forces are equal but opposite. So that means the bug also hit your car with a force of 1,000 Newton. Okay? So the force is equal. They are in opposite direction, but they are equal. So which force is bigger? Well, they're the same. Okay? So action and reaction force pairs are always the same. But which object will have greater acceleration? Now, what does that mean? That means, okay, when they run into each other, right? Which object, so the truck or the bug, will accelerate, which means they will change direction, change speed more. Now, from everyday life, you know that the car will barely slow down, but the bug will most likely fly. Now, if the bug is lucky enough, it will just bounce off the car. If it's unlucky enough, it will actually just get crushed on the window, right? So let's assume that the bug is lucky enough that it's just bounce off the car. So I mean, this is logic, right? That's what usually happens. The car barely slow down, and the bug is like bounce off completely. Now, of course, the reason why this happened is because the mass difference between the two objects are very, very big. So the more massive object feels less of effect than the lighter object. Now, if you have a semi-trailer hitting, let's say, another smaller car, then the mass difference is not that great. Then both objects will feel a huge acceleration. So which object has greater acceleration? Well, the bug. The bug is going to bounce off with a very, very big acceleration, but the truck will barely slow down. Now, why would that be? Because you have to remember Newton's second law. So if there's a force on the object, so there is a force on the bug right now because the truck hits it. There is a force on the truck right now because the bug hits it, right? So mass equals to ma, right? So if the mass on both objects are the same, okay, but the mass on one of the object is very big, then the acceleration must be very small. Okay, like it must be. So because the mass, if the mass of the truck is much, much, much greater than the mass of the bug, okay, then the acceleration of the truck will be a lot smaller than the acceleration on the bug. Okay, because when you multiply the mass and the acceleration, they have to give you the same number. Now, in our example, we set the number to be 1,000, right? So think about in this situation, think about what happened if you actually put numbers into it. So now they're both going to, so for the truck, right? So for the truck, we can do that calculation. F-flat equals to ma to try to figure out the acceleration. Then you will put 1,000 Newton here, and then 2,000 kilogram here in the location where the kilogram is. Now, how do you get acceleration? You divide both sides by 2,000, right? So the acceleration for the truck is going to be about, let's say, 0.5 meter per second square. Now, but if you do the same calculation, but don't do it for the truck, do it for the bug, then the result is very different. Now, you're still doing F-flat equals to ma. Yes, the force is still 1,000 Newton because equal and opposite force, right? Okay, equal but opposite force. But the mass of the bug is a lot smaller. The mass of the bug is only, let's say, 10 gram, right? 0.101 kilogram. Then, if you do this, and you find the acceleration on the bug, so you need to divide both sides by 0.01, which is multiplying by 100. Then you get an acceleration that is 100,000 meter per second. Okay, so the math or the physics works out this way, right? Even though you have the same force between the two people, between the two objects, but the object with the very, very small mass is going to accelerate a lot faster. So that's why, like, if you go up against the train won't slow down. You will just bounce off because the train is a lot more massive than you. So, for example, like in the Marvel movie, right? The Incredible Hulk is charging toward you, and the Incredible Hulk is a lot more massive than you. So what happens? You bounce off. But then if the Incredible Hulk is going against, let's say, like, oh, actually, I can't make that example because I think the Hulk can actually win against like most living things. In the comics, right? The Hulk is so powerful that it can actually win against most living things. So let me use another example. So for example, like an elephant is charging toward you. So you against the elephant, you lose. So your acceleration is going to be greater than the elephant. So the elephant slows down, barely slows down. You bounce off really quickly. But then if the elephant is going up against a killer whale, walking killer whales, I guess, then the killer whales is going to win. The elephant's going to bounce off. So it depends on the mass of the object. Okay, so now knowing this law, which is Newton's third law, action and reaction force. So you can make an argument that, when you accidentally punch someone, the force applied to that person's face from you is exactly the same force that person's face is applying to your fist. That force is equal and opposite. Okay, now remember, I think we mentioned it during yesterday's Zoom meeting, is that the only reason why there is a difference in this level of pain, even though the force is exactly the same, is because of the amount of pain receptors that is in your hand versus the amount of pain receptor that is in that person's face. So you don't feel a lot of pain with your hand. I mean, this is like our hand is a lot less sensitive than a lot of the other body parts that we have because we use our hands to touch, to do most of our daily tasks, right? So it can be too sensitive. Otherwise, you will feel like every little bit of pain, which is very annoying. So then we're going to conclude this with a few more example. So just finding out the action reaction pairs. So when you fire a gun or an arrow or cannons, right, there's this thing called recoil. Okay, so now basically that means the gun pushes the bullet, but the bullet also pushes the gun. So if you imagine that you have a gun with a bullet inside, so there's some like explosive. So basically, the bullet goes out because there's an explosion inside the guns, right? So the bullet goes forward. So let's say there is a pi force on the bullet going forward from the gun. So let's say that's like 1,000 Newton. Then there will be a equal but opposite pi force on the gun moving backward. Okay, same thing. 1,000 Newton, for example. So it will be equal but opposite. So the bullet, so the gun pushes the bullet, and then the bullet in turn pushes the gun. So that's why the gun will actually recoil and travel backward. So what happened is that the speed of the bullet is really light, right? A bullet is maybe a couple, maybe a few hundred grams. The gun is a few kilograms, so it's like 10, 20, or even 100 times sometimes if you're using like a big gun, heavier than a bullet. So therefore, the bullet, even though they both experience the same force, the bullet is going to accelerate and get up to speed a lot faster than the gun. Now the gun will also move, but it will move backward because remember the force is equal but opposite direction, right? And so if you're not careful, the gun will actually hit you. So let's say you're aiming with the gun right in front of your eye and then you try to fire a shot without proper training. What happens is that a lot of people will not expect the gun to fly backward with such an incredible speed that they couldn't hold on, and the gun will hit their face. Okay, you can search on YouTube for like funny like people gun recoil fail video. Yeah, it shows you a lot of people firing like a gun without proper training, and sometimes the recoil is so great that they dislocate their arm or they hit their face. very, very hard because the gun is falling backward. Okay, so now, same thing in here. This one we can actually draw it too. So your hand is applying a force to the brick, right? So why does it hurt on your hand? Because the brick is also applying a force on your hand, which is, the normal force, right? It's the electron of your hand repelling the electron of the brick. Okay, and they're equal and opposite. Now, okay, so hand hits brick. Okay, so brick hits hand. So now if you're hitting someone's face, then, of course, your hand wins, right? Because that other person is going to cry because their face has a lot more pain receptor than you do. But when you hit a brick, the brick is an inanimate object. It doesn't know pain. So who hurt? You. So that's why I always say anyone going up against an inanimate object is always going to lose. So when you're angry at something or someone, some people do that, right? They will hit the wall. They will, kick some furnitures. Usually who end up crying at the end? The furnitures? The wall? No, you. You kick the furniture and then you hurt yourself. You punch a table and then you hurt yourself, right? So let's say you're playing, PUBG, you're playing like League of Legends, you lose a game, you punch your computer. Who end up hurting at the end? Okay, maybe you break the computer, but I'm sure the computer doesn't cry. Okay, you. Human flesh versus inanimate object, equal force, opposite direction, but one feels pain, the other one is not alive. You always lose, so don't do that. Like what has the furniture done to you, right? I mean, you lost the game, it's not the computer's fault. It's your problem. Okay, don't take it out on the computer. All right, now finally, Newton's third law also explains why we can actually have things like rockets. So now, rockets actually fly because they propel something backward. So the fuel inside, once it's ignited, right, the solid fuel is going to turn into a gaseous state. So when solid turns into gas, it expands in volumes, right? And the rocket is structured in such a way that there's only one opening at the end. So when the solid or liquid fuel inside the rocket get ignited by fire or other means, it turns into a gas form and it rapidly expands in volume, and the gas has nowhere to go, so the gas has to go this way, out of the rocket, because that's the only hose, right? So technically, in this case, what happened is the fuel is pushed out of the rocket, right? So this gas, right? So you have this gas that's coming out. Okay, so you have this gas that's coming out. So this is like the force that the rocket applies to the gas, throwing it out. Now, and at the same time, the gas also apply a force to the rocket, because always you cannot apply a force to something without that object applying a force back to you. And this is going to be the reactionary force on the rocket. So the rocket pushed the gas pushed the rocket. Therefore, the rocket flies forward. Okay, so rocket pushes gas, which is the fuel after it turn into a gas. Then the gas, right, pushes back the rocket. Okay, so for example, in space, so let's say you have a rocket and you want to turn right? So think about it. So let's say you have a rocket. So let's say the rocket is exactly, this kind, the one that is in the picture. Oops, I cannot draw a rocket. There you go. Okay, that's best. Okay, that's good enough. Okay, now, so here's your rocket, right? Okay, so now let's say it has some little mini rockets in these locations so that it can shoot out gas, right? So you know how a spaceship actually turns is by shooting out gas from various different parts of the spaceship. So it shoots out gas not from the bottom only. It also shoots out gas from the top sometimes. So for example, if I would like to turn, so let's say this is a little rocket A and this is a little, mini rocket B. So if I want the rocket to turn right, which way should I fire the rocket? A or B? If I want the rocket to turn right. Okay, so if I want the rocket to turn right, I'll actually fire rocket A to the left hand side. So if you do, when you do that, right, the rocket is gonna push the gas out to the right hand side, but then that also means the gas is gonna push the rocket to the left hand side, and then the rocket will turn. Okay, so the gas pushed the rocket to the right, the rocket pushed the gas to the left, and the rocket end up turning right. So every time you try to make a direction change, you actually need to fire a tiny little propeller in the opposite direction that you wanted to go. Okay, which is, if you want to go forward, fire a propeller that points backward. If you want to turn left, fire a propeller that turns right. Okay, so now that's it for this lesson. So this lesson is mostly just concept. So that's why the worksheet associated with this is also just a lot of explaining and concept and trying to apply these laws to everyday life. Okay, so I will put all the required question on the homework page. This lesson is very short, so you should have a lot of time to do some of the worksheets. So there are at this point, I think like 3 worksheets in total. So I'll pick a few questions from each of them. But I would say that the question, a worksheet number 1 and 2 is probably the most important one. So you should really try more than what is required for hand in for submission. For some homework submission, please submit it on Moodle from now on. We are no longer going to use the portals when Moodle is now working for us. So there will be a link that says dynamic video day homework check 1, and then you submit your homework questions over there, right? Okay, so have a nice day, everyone.